Hey guys, it's Mr. Morse. We're going to go through a different topic each week related to reactions. This week's it's looking at the different types of reactions and kind of reviewing back through what that means in terms of balancing them. So what we're going to be looking at is we're going to go through a PowerPoint or some Google Slides here. It's also linked directly on the document, so you can check it out and just click through that as much as needed. But I'm going to try to make sense of this and go through it with you. If you need some more explanation, there is another video or another set of videos linked on Wednesday's e-learning assignment. And I'll also be doing Zooms each week, so you can check in with me then as well. So let's check this out. So when we're looking at reactions, there's 5 basic types of reactions. There are more that exist in the universe. There's different ways that you can put these together, but these are the 5 that we're going to learn about. So synthesis, sometimes you'll hear that referred to as combination, decomposition, combustion, and single and double replacement. And what we're looking at to figure out which type it is we're looking at what reactants we have, we're looking at what products we have, and we're seeing how those are different. So we'll define each of these, we'll do some examples, then we'll get into balancing. Oops. There we go. I like that a little bit better. Sorry. So synthesis, first and foremost, is another way of saying a combination, or we take 2 things and we put them together in one. So with synthesis, a real key is that you end with just one thing. So for each, we'll start with a general reaction with some generic letters, not referring to elements, and then we'll see some examples where that falls with some real elements. So here we have 2 elements or compounds that combine into just one product. Anytime you have just one product, no matter what the coefficient is, that's going to be a synthesis. So that's the easiest clue. The other thing is you've got 2 things coming together. So here, hydrogen and oxygen making water, or calcium oxide and water making, in this case, calcium hydroxide, 2 into 1. Decomposition is the opposite of that. It's the easiest to recognize by looking at these things because we're starting with just one thing. One thing breaks into more pieces. We will always focus on it breaking into 2 pieces. Some reactions can actually break into 3 or more pieces as well. So with a decomposition, we are one reactant, that's your key, breaks into, it does say 2 or more. Here we're focusing on just 2 products. So here we have sodium oxide. It makes sodium and oxygen. So a compound can break down into its elements, or we can have a compound like, in this case, it's nitric acid that breaks into 2 other things. In each case, I think we've written them correctly. In addition to just having the right things on the left and the correct things on the left and the right side, we also want to make sure that we're thinking about balancing. So we have 2 H's and 2 H's. We have 2 going to my N's. I have 2 N's. And then I have 2 times 3. So I have 6 O's. 1 plus 5. That's where my 6 O's come from. So over here, I have my reactants that's turning into products. And it's still the same elements, just combined in some new ways. A combustion reaction is a little bit more specific than this. Synthesis, decomposition, single and double replacement can really be combinations of almost any element on the periodic table. But the combustions we're going to look at or call combustions just have 3 elements in them: carbon, hydrogen, and oxygen, and they always make the same 2 products, carbon dioxide and water. So if you see CO2 and H2O as your products with carbon and hydrogen on your left side, that's a combustion. So a hydrocarbon, which is a generic term for anything made of carbon and hydrogen, reacts with oxygen. It's always going to be the oxygen in the air, so it's O2. It makes CO2 and H2O. From there, you're just going back and forth and balancing it. So we will be talking about balancing and skills for that later, but balancing is kind of just a game of guess and check. Well, how many are here? Make it the same on the other side. How many of this are here? Make it the same on the other side. And then you just kind of keep going back and forth, checking and double checking until it works out. You can see here there's something that has carbon, hydrogen, and an oxygen mixed in, but we're still going to call that a combustion. Really, anytime anything burns, it's combustion, but we are going to reserve the term combustion for when it's hydrocarbons or hydrogen and carbon making CO2 and H2O when it burns in oxygen. Oops. Let's go to the next guy. Single replacements, and you'll see that abbreviated as SR, is something where you have a compound. So we've got some compounds here, and elements by themselves. And what comes in is the A goes in, and the B gets kicked out by itself. Or X comes in, and Y gets kicked out by itself. There are some rules to how and why this happens that we'll get into as we write equations and as we predict products. But for now, we're really just looking for some element that's by itself reacting with the compound, and then something that used to be a part of the compound is kicked out, so it's a lone element, and then we have a new different compound. Sodium was by itself, here it's in the compound. Copper was in the compound, it got kicked out by itself. Down here, we have potassium and bromine are together with fluorine by itself. Now potassium's with fluorine and bromine's by itself. We'll notice here and talk about it again later, but it's good to hear it a lot of times, that the sodium and the copper are what are trading partners or places here. Those are both metals or things that can form cations. Here, fluorine is a halogen, so is bromine. Those are both things that are going to be negatively charged anions, so the anion will replace the other anion. But when you're just trying to figure out the type, you don't even need to think of it in that much detail. Element compound, different element, different compound. Double replacement, or a DR, we have a compound, and then they swap partners. We'll talk about this and kind of think about it in some different ways, but it's kind of like a double date where we're switching partners here. They've done that enough in different sitcoms and romantic comedies where you get the idea the people aren't matched up right, and so they go with the other one, and then that's the person they end up dating or marrying down the road. In a real reaction here, we have two compounds that switch partners, or switch the ion that they are with to make two new compounds. Sodium used to be with hydroxide. Well, now sodium's with sulfate. Copper used to be with sulfate. Well, now copper's with hydroxide. So they just swapped partners. Cation here goes with this anion. The cation here goes with this anion. But really, we're just recognizing two compounds, two different compounds. And if we think about this, connecting it maybe to some math classes, if you are foiling it, first outside, inside out, last, here are two outside things. The sodium and the sulfate will go together. Our copper and our hydroxide, our inside, go together. This one's a little bit different version, but the same idea, where we have a compound and a compound, new compound, new compound. It doesn't necessarily look like the outside things, but really here the hydrogen and the hydroxide, H and OH combine to make H2O. And sometimes when we're balancing, it's really helpful to maybe go one element at a time. Sodium, oxygen, hydrogen, copper, sulfur, oxygen, copper, oxygen, hydrogen, sodium, sulfur, oxygen. Obviously, you can list elements like that as well. But it's even easier at times to think of, well, I have a sulfate, an SO4 here and an SO4 here, an OH here and an OH here. Well, that's why I needed a 2, because there was a 2. The one copper to the one copper. And when we're looking at it with polyatomic ions instead of individual atoms or elements, hydrogen, H, combines with hydroxide, OH, and it makes HOH, or it makes H2O. So that's kind of a weird but unique version there. So those are our 5 types. Here I have only, it says just from the products. I meant just from the reactants. But without even knowing what they turn into, we can think about, well, is this something breaking apart, things coming together, things swapping partners? So the first one's the easiest. We have just one thing. The only thing that can do is break apart, which is why our first is decomposition. And really, for our first set of skills here, you're always going to see what your products are. So it'd be pretty quick and easy to know, oh, one thing turning into 2. Here in our second example, we have an element by itself. That is Al, not Ai. We have a compound, HF, element and compound. The example or the type that meets that is a single replacement. The element will come in and kick out one of those, so we'll have aluminum bonded to something, and then hydrogen will end up by itself. Here I have sodium and oxygen, element and element. There's no way that they can switch partners around or do any sort of trading there. So this has to be, the only way they can do anything is come together. So that is a synthesis. Here I have a compound and another compound. So compound and compound is always going to be double replacement because you're always switching partners. Element and compound here. It is very similar to up here, but different version of it. Element and compound will make a single replacement. So sometimes you can look at both reactants and products, but you can even just look at sometimes just reactants, sometimes just products, and even know what is what. Your last assignment before break was about balancing equations. We hadn't really specifically taught that. You may have seen that before in biology and ICP in middle school, but just wanted to kind of make sure that we did understand some definitions there. Balancing equations is all about the law of conservation of mass, meaning that we start with the same elements we end with. We start with the same number of atoms that we end with. And it's important to know that we have two different sets of numbers that help us to do that. The subscript is the number that goes in the formula. We worked a lot on subscripts when we did ionic and covalent and acid naming in Chem 1. That was just what subscript goes down on the bottom. And when we were reviewing names and formula writing through all of the mole unit, when we were doing our benchmarks, it was all about that as well, making sure we knew what subscripts go where. The new or different thing is a coefficient. Now that we have a full reaction and reactants turning into products, we want to make sure we have the same number of atoms of each element in our reactants and in our products. And the way we can do that is by putting a number in front of it. That is a coefficient. So we saw those were there in the reactions we just looked at. It was the number in front, and that number gets distributed. It's saying that I have 3 of this whole set of H2Os, or 3 sets of 2 hydrogens, which is where the 6 down here comes from, and 3 sets of 1 oxygens, which is where that 3 comes from. So when we balance an equation, the formulas are already written. We do not change any of the subscripts. We can only put things in front. And the concept builder that you already did, some of the other concept builders in practicing that we're going to have you do this week, have you do it that way, where you can't change any subscripts. We're really only putting numbers in front. And even when you get to the Canvas quiz at the end of the week, you're going to see that as well. You should only be changing the coefficient. We're always going to throw some wrong answers in there that might have the subscripts changing, but that would be a totally different reaction with different reactants and products. So it's all about changing those numbers in the front. So here there's some balancing. Balancing, like I said, is a game of kind of guessing and checking. Once you've done a lot of balancing, you kind of get some skills, but really you're going one element at a time. How many are here? How many are there? How many of this are here? How many of that are there? How many of this? How many of that? And as you go back and forth, sometimes you have to kind of start over or check or change your answers. And sometimes you can get it right on the first time. We balance one atom and one element at a time. And you can put a number 1 anywhere when that's already balanced. Or what you'll see me do and what you'll see on some of the practice we have you doing is if it's just blank, then that implies or it means that there's already a number 1 there. So in this first one, we have calcium chloride, 1 calcium, 2 chlorides, lithium oxide, 2 lithiums and 1 oxygen. On the right side, we have calcium oxide, 1 and 1, and lithium chloride, 1 and 1. So we've got some numbers on the left that aren't duplicated here on the right. So with our calcium chloride, we see 1 calcium, 1 calcium. We don't need to make any changes based upon that, but we've got 2 chlorines here, but only 1 over there. So the first coefficient we would try would be putting this 2. By putting that 2, now I have 2 chlorines and 2 chlorines. And as I keep going, I see, well, I'm supposed to have 2 lithiums. Good news. We just put a 2 in front of the lithium. 1 oxygen, 1 oxygen. So as you're balancing an equation that's already written, it has to work out. there has to be a way that you can put whole numbers. We're always going to use whole numbers in those blanks, either ones, twos, threes. Sometimes you can get up to double digits, but most time it'll be single digits, usually 5 or less, in front of your numbers and get it to balance. Our next example here has aluminum sulfide with some subscripts reacting with copper. It makes copper sulfide and an aluminum. So I'm going to go back and just mention compound, 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 double replacement, compound element, single replacement. But I do have subscripts on the left that aren't matched on the right, which means I will need some coefficients. I start right away with the first thing I run into. It's really easy to just go left to right. If something appears more than one time in a compound, in an overall reaction, it's usually easiest and best to do that last. And I don't know that I set up any examples like that, and I apologize for that, but you'll kind of see it as you do your own practice. But I've got 2 aluminums here. That's not balanced. So then when I put a 2 in, my 2 aluminums and my 2 aluminums are balanced. My sulfur was a 3, which is why I dropped a 3 in right there, because I need that sulfur to balance. It did throw off the copper, but I'm just dealing with one element at a time and then kind of going back and changing things as needed. So now my aluminums are good, my sulfurs are good, but my copper's a 3 versus a 1, which is where I end up with the coefficient there. So this one ends as a 1. All of these blanks are still 1s. This bottom guy, as I creep down to the bottom, it's going to keep pulling that up. So I'm going to stay off the bottom. But I have sodium phosphide, magnesium bromide, magnesium phosphide, and sodium bromide. We can see there's subscripts on the left not matched and mirrored on the right. So we're going to do some back and forth here. And I'm just going to go in order. We're going to see what works, what doesn't. 3 sodiums on the left, so I drop in a 3 on the right. So now my sodiums on the left, my sodiums on the right are balanced, which is awesome. The problem with that is if I was going to look then right away at my bromine, I have a 3 there. Over here on the left, I've got a 2. So we run into this issue. It doesn't work to balance the bromine in that way. This can't be a 3 because that doesn't give me an even number on the left. That'll happen from time to time. And when you get into the situation where it's even on one side and odd on the other, the strategy is always going to be the same. You kind of start over by doubling everything. So what I did there, and as soon as that pointer goes away, you'll see I doubled my sodium phosphide. So down there at the bottom, there's now 6 sodiums on the left. So I got to 6 sodiums over here on the right. And my question mark in front of the magnesium bromide can now become a 3. And as I do that, I have 6 sodiums on the left, 6 on the right. 2 phosphides on the left and 2 on the right. That balances that one. 3 magnesiums on the left, 3 on the right, and 6 bromines on the left and on the right. So although this was kind of a quick overview of everything, the goal or the hope was that each of these things were easy, and I didn't want to kind of do too many examples or just spend tons and tons of time on something when you have this video that you can go back and look at later. So watch the video as many times as you need. There's going to be some more videos linked on Wednesday's e-learning assignment. I will on Wednesday have a Zoom session if you're kind of stuck, whether it's types or balancing. But you're going to see some concept builder practice, another practice quiz, and then on Canvas quiz that we're going to have at the end of the week, you're going to get multiple attempts in case something comes up that's tricky. But if you get stuck on that Canvas quiz, don't just blow through all your attempts. Go back, watch one of the videos, do another set of practice, or reach out with some questions. So that's it. Wanted to do a quick overview here. Each week, we're going to add more skills to it. So make sure you're really getting this stuff down. You're practicing and you're reaching out with questions when you have them.